Thank you, Martin, and thanks a lot to the organizers for giving me the opportunity to speak here. So this work is done in Saclay, the Cavitronics group, and this is a collaboration with the group of John Morton in London, UCL London, and theory by Klaus Möllmer's group in Aarhus University, and also collaboration with Renbao Liu's group in Hong Kong. So the focus of this work is really the fact that magnetic resonance, and this is the photograph of a commercial Bruker EPR spectrometer, is of course a fantastically useful technique, but as we heard yesterday from the talk on NMR, it suffers only from the low sensitivity issue, which means that only macroscopic samples can be measured. And of course, this has triggered a lot of efforts to improve the sensitivity of magnetic resonance. And here I have listed maybe three ways that, in fact, the sensitivity can be enhanced so much that even single spins can be detected. This can be done optically. This is an example for NV centers, for instance. The magnetic resonance of individual NV centers can be measured routinely. Also, scanning probe techniques can be used. And in fact, even scanning probe NV magnetometry can be used to reach single spin detection level. And finally, electrical detection also is a very sensitive technique, EDMR. Now, we have chosen a slightly different approach, which is to rely on techniques coming from the field of superconducting quantum circuits. This is a field known as circuit quantum electrodynamics. And if you want, Circuit-QED means essentially superconducting qubits and circuits. This is really what it means. And our approach, because we come from the Circuit-QED field, is to apply these techniques to magnetic resonance and to, in particular, the problematic of doing sensitive electron spin resonance detection. And so I will, in the first part, I will describe a bit the principle of how this works. And I will try to focus on two applications, which is to show that this can be used for sensitive nuclear spin detection. And also, I will discuss the application of Circuit-QED to a novel electron spin hyperpolarization scheme. So let me start by just reminding you how a usual electron spin resonance spectroscopy works, or maybe magnetic resonance in general. So this is really a conventional ESR inductive detection of magnetic resonance. So we have our sample containing the spins. It is placed in a magnetic field B0, which polarizes the spins and give them a certain Larmor frequency. This sample is enclosed in a microwave resonator, which is probed by microwave pulses. And if the spins are on resonance with the cavity, the microwave is at the resonator frequency, and then this microwave pulse can excite a pi/2, can produce a pi/2 rotation for the spins. After this first pi/2 pulse, which can be done rather quickly, there is a waiting time. During this waiting time, all the spins will process at a slightly different frequency because of inhomogeneity inside the sample. So this transverse magnetization, which has been created by the pi/2 pulse, decays actually to 0. But this can be refocused by a pi pulse. So this pi pulse is applied some time tau later. And this pi pulse acts as a time reversal symmetry, and in fact, brings the spins to refocus and to recreate a sizable macroscopic magnetization, which then leads to the emission of a microwave pulse, and this pulse is called an echo. And this spin echo, this is the Han echo sequence. This is not novel. This dates from the 50s, I think, really, this principle. And the spin echo sequence really contains all the information on the spins, and this is what you want to detect. Now, how to improve the sensitivity of this spin echo detection-based method? Well, sensitivity means signal to noise. So to improve the sensitivity, we want to increase the spin signal, the spin echo signal, and decrease the noise. So the way that Circuit-QED can help you do this is described on this graph. And this is very simple. First of all, we do our experiments to very low temperature, millikelvin temperatures. And this has two consequences because we work at 7 gigahertz. So at 7 gigahertz and 20 millik, all the spins are in their ground states. So this means that the spin polarization is maximal. This is good for maximizing the spin echo signal, which is proportional to the average polarization of the spin ensemble, right? But this has also another consequence, is that the thermal noise, which is present in the detection chain, is also suppressed because now there is no thermal photon at 7 gigahertz. Only quantum fluctuations of the microwave field remain. And so, in fact, this means that this is kind of the best you can do with simple techniques. Another aspect, so now this is kind of trivial, but now Circuit-QED gives you another tool, which is very interesting, is these superconducting micro-resonators. So now imagine you replace this like kind of volumetric cavity around the spins, the sample, by just a thin film resonator such as this one. So you see this is, now the resonator itself is this little dark area which represents a superconducting thin film deposited on top of the substrate. So imagine this is a capacitor, you see, it's just fingers facing each other, and then this is shunted by a wire. So this is a LC circuit. Now this LC circuit here, the inductance can be very narrow. So now we have a much stronger confinement of the microwave field, which will be really the magnetic field generated by this resonator around the wire will be strongly confined. This is near-field microwave optics. And so this is plasmonics, really, microwave plasmonics. And so you can have very strong confinement of the field. And this leads to an increase of the microwave to spin coupling G, and therefore a higher spin echo signal. Now, in addition, if you do that with just normal state metal, the losses, the ohmic losses in the film will be such that the Q will be maybe 10 to the -5. But with superconductors, you have no dissipation, so you can have high quality factor together with this strong confinement. This is really the key advantage of these techniques. Finally, Circuit-QED also provides a new tool, which I would like to advertise here. It's not really new, but it has been developed in the last 10 years. This is the Josephson parametric amplifiers. These are superconducting microwave amplifiers that are based on Josephson junctions. Here, this is a photograph of a device that we have done in our group. It's again, in fact, essentially an LC circuit. I mean, all we do essentially are LC circuits in this field, but combined with an array of squids. And now, if these squids are pumped at twice the resonance frequency of this circuit, there will be gain, and this gain is actually very low noise. In fact, in certain conditions, if this is in the so-called degenerate working regime, this is a strictly noiseless amplification of one of the field quadratures. All right, so this is a photograph of a typical setup. So this is, in fact, a photograph of a dilution refrigerator, really. This is a 4K stage, and here, all that we do is at 10 millik, and all this is at 10 millik. Here you see a photograph of the sample holder, which is inside a homemade two-axis Helmholtz pair of coils. And the sample itself is, you see, is on this chip here, which is small. You see 3 little circuits, and these are the resonators. Now, this chip is enclosed in a copper sample holder, which is then connected to microwave cables, which are used for measuring. Okay? And this is an example of a resonance. You see, this is measured in reflection, and you have typically quality factors of at least 100,000. And this is, again, a schematics of the experiments. So the resonator with the spins are here, and the input line is heavily attenuated because we want the microwave field to be in the ground state. We want the noise to be completely suppressed to get better sensitivity. And therefore, we attenuate at low temperatures. This is the only way to do that. And finally, this input signal is sent to the cavity, and the output signal is first routed to this parametric amplifier, which is also at 10 milli-K. And then it is powered by some microwave signal. And finally, the amplified signal goes out of the fridge, is first amplified at 4 Kelvin, and finally at room temperature, followed by standard homodyne demodulation. Okay, so I just want now to say a few words on the spin system that we use in this talk. We do experiments with various spin systems, but here all the results that I will present are obtained with donors in silicon, and in fact bismuth donors in silicon. So now in the silicon lattice, you imagine that you replace one silicon atom by a group 5 element, such as phosphorus, arsenic, or bismuth. Now this will create 4 covalent bonds with the other silicon atoms, but there is an extra electron, and this extra electron at room temperature is ionized. It goes in the conduction band of silicon. But at low temperatures, if we cool down, this electron can be trapped. There are some energy levels associated with bound states around this ionized bismuth atom. These are low, these are only a few tens of milli eV, so you need to cool down. But at low temperature, an electron can be trapped around the bismuth atom. And now this electron is unpaired, and it has an electron spin resonance signal. And the Hamiltonian of this system is arguably the simplest that you can encounter in EPR spectroscopy. It is just a Zeeman term for the electron. But then there is also a nuclear spin associated to bismuth. And this nuclear spin has a Zeeman effect. And there is also a hyperfine, an isotropic hyperfine interaction between the electron and the nuclear spin. So, okay, so it's a little bit complicated because bismuth has actually a spin 9½ so there are lots of states, but that's okay. And so we can diagonalize this system. And in fact, in the low field regime, this Hamiltonian is dominated by the hyperfine. And so at strictly zero field, only this term exists. And so we have 2 multiplets of states which are degenerate, one with 9 states and another with 11 states. And when you apply a small magnetic field, this degeneracy starts to be lifted. And so we have these 9 and 11 states that appear. And this gives rise to a number of allowed transitions in the 7 gigahertz range, which are shown here. And so basically the experiment is that we have our sample with the spins, the resonator on top, and we apply a B field parallel to the surface of the sample. And so we can move in this diagram, and at some point the spins may be on resonance with the resonator. So I forgot to say that the bismuth atoms are implanted in a very shallow manner at 100 nanometers below the surface, typically. And when the spins are on resonance with the resonator, we observe a spin echo, as shown here. These are the typical data that we obtain. You see here the 2 control pulses, and then with the waiting time. And this is not a pulse, this is the echo coming from the spins. And we integrate this echo, and this is the signal that we are studying. Okay, so so this is really like standard magnetic resonance. In this domain where the coupling of the spins to the resonator is unusually large, there is a new phenomenon that we have observed 2 years ago. I mean, it's not a new phenomenon. It was predicted by Ed Purcell in 1946, but we've been the first to observe it in the spin system. Of course, this is a phenomenon which is well known with atoms, is the fact that the spins can now relax by emitting spontaneous emission of microwave photons in the cavity. Usually in magnetic resonance, spins, the relaxation time of the spins is governed by interaction with phonons or with other spins. But here we have a situation where this other relaxation channel, which is just the fact that the spin can relax by emitting a photon inside the cavity mode, becomes in fact the dominant relaxation mechanism. And this is evidenced by this curve, which shows the effect quite clearly. This is the measured relaxation time of the spins as a function of their detuning to the resonator. And you see that at even a few megahertz detuning, this relaxation time reaches thousands of seconds. And as soon as we put the spins in resonance, it goes down to 1 second. So this is a very strong effect, and it's by far the dominant effect for spins resonant with the resonator. Now, in fact, this is now we use nowadays we use this phenomenon, in fact, as the best way for us to extract experimentally the coupling constant between the spins and the photons, because this per cell relaxation rate at resonance is very simply expressed as a function of the quality factor of the resonator, its frequency, and the only quantity which comes in is this coupling constant G. This is the single spin, I really have to emphasize. This is the coupling within a single spin and the resonator. It's not an ensemble. And so in this example, the coupling was 60 Hertz. Now 60 Hertz is good, but we would like to have stronger couplings, and we have been a bit obsessed in the last years with trying to go to higher couplings by reducing the magnetic mode volume precisely to enhance the coupling. So in this first experiment that I've shown, we had a wire with a length of 1 millimeter and a width of 5 microns. So this produces such a pattern, and it's a volume of 20 picoliters. And then progressively, we have narrowed down and shortened this inductance, first with a wire of 500 nanometers width and 100 microns long, and now in our most recent device, 100 nanometers wide and 10 microns long. And so correspondingly, we observe, and for each geometry, we have measured this spin echo and spin relaxation. And we now, using this spin relaxation measurement to extract the coupling, we have gone from 50 Hertz to 400 Hertz and now 3 kilohertz. And the sensitivity, so correspondingly, the sensitivity that we obtain here in this first experiment was 2,000 spins per root Hertz, which was already a 4 orders of magnitude improvement over the state of the art. And now in the latest experiments, we have a detection sensitivity of 10 spins per root Hertz, which means that in 1 second integration time, we have enough signal-to-noise ratio to detect a signal coming from 10 spins with signal-to-noise ratio of 1. Okay. So, okay, so that's good. So going to small mode volume definitely increases the sensitivity. However, it comes with other unexpected and unwanted things that we have encountered. And I don't want to spend too much time discussing them, but at least I wanted to show them to you. That in fact, these small size and small devices, they come with some effect on the spin line width and the spin coherence time. And not everything is clear, but let me show you first the data. So in this first geometry where we had a 5 microns wide wire, these are the lines that we measure. So you have to imagine, here I'm sweeping the magnetic field, and we expect, so this is in fact one resonance, and this is another one. So really we would expect only one peak here and one peak here. This is not what we observe. We observe this weird shape of 2 split peaks, and here again. So that's one thing. So on this device, we had a T2 of 9 milliseconds. So T2 is the spin echo coherence time, right? 9 milliseconds. And then when we go to narrower and narrower lines, inductances, we see that everything becomes even worse. So this line width now in this intermediate device, we have spins everywhere, essentially. There is some kind of resonance peaks, but it's even hard to attribute to anybody. And the T2 has gone down to 2 milliseconds. And in this last device that I showed with 100 nanometers wide width, wire, we don't even see a resonance. There are spins everywhere. So this is really weird. And the T2 has gone down to milliseconds or a bit below. And so, so at least we understand part of the story with this broadening, and I just wanted to discuss it here. So what are the broadening mechanisms here? Well, you have to realize that this spin Hamiltonian, so the Zeeman term is pretty clear, but here we have this hyperfine term, and in the hyperfine, there is this hyperfine coupling constant, which depends on the electric field and on the strain to which each spin is subjected. And so now, and I want to insist on the strain, because what happens is that in our devices, we have this substrate of silicon, and then we deposit some metal film on top, and we cool it down. Now, it turns out that aluminum, or in general metals, contract a lot more than semiconductors at low temperature. And so, in fact, we end up with a strain profile which is quite well defined at low temperatures, and which is really due to the differential thermal contraction of the two materials. And this means that we have spins that are below the wire, which are compressed, essentially, and the ones which are stretched. And in fact, we have done measurements independently of this, this we have done together with John Morton an analysis of measurements of the response of donors in silicon to strain, and we have shown that the response was linear in strain, in the hydrostatic strain applied to the spins, and we have even calibrated this constant. And now, using this, it's actually tempting to attribute these two peaks to these two family of spins, one that are below the wire and one that are just outside the wire. So it's tempting to do that, but it's actually we have really gone a bit further than that. We have really tried to reproduce ab initio the measured spectra that we have. So this is a broader range of peaks on a broader magnetic field scale. And I don't want to enter into the details, but the only thing I want to say is that what we have done is to calculate the strain profile using finite element simulations, deduce the hyperfine shift using the calibrations that we have done, and then finally simulated the expected spectrum without any adjustable parameter. And I was quite surprised how good, it's not perfect, but how good the simulations reproduce all the weird features that we observe in the measurement. So at least, so this is for one device with this 5 microns wide wire. And so we really have a quantitative understanding in this device. However, the agreement becomes only qualitative in the other devices. I didn't show the data here, but so it might be that we are also witnessing extra shifts due to stray electric fields. And so this is now here I'm speaking of the line widths, but there was also this question of the reduction in coherence time, the T2. And this is another story. And here we really don't know what is going on. I mentioned that T2 dropped by 1 order of magnitude between the 5 microns wire resonator and the 100 nanometers wire resonator. And it's even worse than that, in fact, because the temperature dependence of this coherence time is also very peculiar. And here I'm just showing some data that are very fresh and very preliminary. So don't, and in fact, actually we don't understand them also. So here I'm showing data from a sample in which we have patterned on the same time. So this is the same cool down, two types of resonators, one with a narrow wire of 100 nanometers and one with a 5 microns wire. We plot the coherence time as a function of the temperature. And the most remarkable things, these are 2 points belonging to this resonator obtained in slightly different conditions. But the most remarkable thing is that the T2 changes between 12 and 18 milli-K, and actually drops by 1 order of magnitude at 100 milli-K. And this is very, very hard to understand by any mechanism we can think of. And so this is really unexplained temperature dependence. And there are similar data obtained by Hans Hubel's group in München. And in fact, the other resonator, which is on the same chip, again, the same cooldown, doesn't show this at all and has this 1 order of magnitude longer T2 and shows a different, very different temperature dependence. So there is definitely something weird, some non-trivial resonator-induced decoherence mechanism that we are trying to understand. All right, so now let me go to a first topic that I wanted to discuss, which is to use EPR, because EPR spectroscopy here, I've just shown how to measure electron spins in the sample. But really, the power of EPR spectroscopy is not that, it's how to use these electron spins to access their local magnetic environment by a number of pulse techniques, Endor, Eldor, DIR, ESEEM, etc. And really, you have this electron spin, but maybe you are even more interested in the local environment, these small nuclear spins, and maybe you want to know how many and what are their nature, etc. And so what we wanted to show is that we were able to do this. We are not only able to do stupid Haneko pulse sequences, but we could also do real, say, closer to real EPR spectroscopy with this strange home-built quantum-limited spectrometer. And the first step in this direction was taken by the Steve Lyons group in Princeton, where they have been able to do Endor also with superconducting microresonators. And we were very inspired by their work. So just a few words on, so what we did was ESEEM spectroscopy. So what is ESEEM? ESEEM is electron spin echo envelope modulation. And to understand ESEEM, this is just a very cartoon sketch of a simple situation where you have an electron spin S coupled to a nuclear spin I by some interaction. So there is a certain distance and a certain angle between the two, and they are placed in the field B0. And there is a dipolar hyperfine. So this is just the dipolar interaction between these two magnetic dipoles. Believe me, this is the formula, I think. And now what you have to look at is this dipolar hyperfine Hamiltonian between these two objects. So we have here the Zeeman terms of the electron and the nuclear spins. And then here, this is the hyperfine interaction. And this is separated into a secular part. Sorry, this is still secular. Both are secular, but SZ-IZ term, isotropic part of the interaction, and a non-isotropic part, which is SZ-IX. And this non-isotropic part will give rise to this ESEEM signal. Now, so what is going on? Well, because of this term, the field that is seen by the nuclear spin is not only B0, but is the sum of B0 and the field generated by the electron spin. Now, because of this term, this field is not only along the z-axis, but it is actually tilted because of this field. So really, the nuclear spin quantization axis is something like that here. Now, imagine you do a spin echo sequence. You start with a pi/2 pulse on the electron spin. So suddenly you flip this spin, which means that now the field that the nuclear spin sees is changed because of this flip and this term. And now, which means that now the nuclear spin will start precessing around this new axis. But this precession in term will act on the electron spin. And so now, if the spin echo time is very short compared to this Larmor frequency of the nuclear spin, nothing will happen, not much will happen. But if we are in a situation where the nuclear spin can do a pi half rotation in between the two pulses, then there will be, in fact, a suppression of the echo. But this suppression will be overcome when now the delay between the echo is 2 pi, because then we have the same phases. So essentially what it means is that we expect a modulation of the spin echo amplitude as a function of the time between the pulses at a frequency which is close to the Larmor frequency of the nuclear spins. and a modulation amplitude, which will depend on the ratio between the magnetic field and this magnetic field added by the spin, and so this B term here, and the nuclear spin Larmor frequency. So this means that if we go to very high fields, this effect will be very suppressed because the change here in nuclear spin quantization axis will be very small because B0 will be by far the dominant, right? So what is the case? What is the situation in our sample? In our sample, we have a bismuth donor, which is an electron spin, in a silicon lattice. But in fact, I forgot to mention, but this is a good time to do it, that our samples are in fact silicon that has been isotopically purified. So it consists mostly of the 29 isotope of silicon, which is nuclear spinless. But there is a small remaining residual concentration of silicon-28, which is a spin-half nucleus. But because it's only 0.05%, in fact, the distance between the electron spin and the neighbor nuclear spin is actually quite large. It's really of the order of 7 nanometers. And this corresponds to typical dipolar interactions, which are very weak, really on the order of the kilohertz. So this means that if you want to see the ESEEM effect of this type of sample, you need to work at very low magnetic field. But in our case, this is this broadening of the line actually comes to our help because we have spins pretty much at all magnetic fields, so we can try to work very close to zero field. This is the spin echo amplitude as a function of the field, and you see that we have signal all the way down to zero fields. Although we should not. I mean, really, in principle, if we had no strain broadening, we should have be able to measure only here. But now we can measure, in fact, in all this region. And these are the data. So these are spin echo data observed by just changing the delay between the pulses and measuring the echo amplitude. This is as a function of the magnetic field, and you clearly see this oscillation that enters the data. And so we can Fourier transform this data and verify that this corresponds to the garomagnetic ratio of the silicon-28 atom. Yeah, sorry, silicon-29. I said we had, yes. So silicon-28 is without nuclear spin, and silicon-29 has a nuclear spin half. Yes. And in fact, using this data, we have, in collaboration with Gengli Zhang from Hong Kong, we can fit this data to extract the concentration of silicon-29 nuclear spins. And we find our best fits here between 0.04 and 0.05%. And the nominal concentration that we were given was indeed 0.05%. So this provides, in fact, an independent confirmation of the silicon-29 isotopic enrichment. And let me emphasize that here, this ESEEM signal comes from a very small number of nuclear spins. It's typically 10 nuclear spins for each electron spin. Here we are measuring spin echo from 100 electron spins, so it's really signal from about 1,000 of nuclear spins. I can't resist to show you a little bit of virtuosity in ESEEM. My postdoc Sebastian Probst wanted to go beyond. You see that in this data, the oscillations are not very pronounced, and that's because the T2 of the spin comes in competition. T2 is not that long in this sample, and so it competes with these oscillations. But there are smarter pulse sequences than just a simple echo. There's 3 and 5 pulse ESEEM. So here this is 5 pulse ESEEM. And here the idea is that you convert the coherence into a population of the electron spin. And now the signal is finally limited only by the T1 of the electron spin, which is much longer. And this is why now we can measure up to 50 milliseconds and see very nice oscillation of the ESEEM signal. Here note that the blue is the data and the black is ab initio simulation. It's not a fit. It's really just a simulation. And this very non-trivial shape with beatings is very well reproduced. So this is a bit virtuosity, really. It's just to show that we can really do EPR spectroscopy, pulse EPR spectroscopy. All right, so let me move to my really last topic, where I want to discuss Circuit-QED-enhanced electron spin hyperpolarization. So here, the idea is now so far we have worked at millikelvin temperature, and at 7 gigahertz, as I mentioned, all the spins are polarized just by Boltzmann distribution. But imagine that for some reason you want to work at 1 Kelvin or 900 milliK, also at 7 gigahertz, then the Boltzmann distribution of the spins will give a polarization which is quite a bit reduced. And this also reduces the spin signal. And so in magnetic resonance, this is an issue. And of course, it would be very desirable to polarize spins beyond the Boltzmann distribution at 900 milliK. And so this is called hyperpolarization. And this is a big topic in magnetic resonance, evidently because we want to maximize the signal. And so let me just review a few of hyperpolarization techniques. For electron spins, to my knowledge, this is the existing techniques. The maybe best known technique is optical pumping, which works for certain spin systems, well, spin systems that have optical transitions and an optical pumping built-in mechanism, if nature is good enough to provide it. So this is, of course, the case of NV centers in diamond, where by just shining green light, you can pump all the spin population in the ground state to ms equals 0. And also spin-dependent tunneling phenomena in transport measurements lead to electron spin hyperpolarization mechanisms. Now, for nuclear spins, the situation, really the technique to hyperpolarize nuclear spins is called dynamical nuclear polarization, DNP. And this is a very, very important technique, even commercially. It's a very, very big field of research. And here, this relies on the fact that in the same sample, you have both nuclear spins and electron spins. Now, at the same temperature, same magnetic field, nuclear spins have a frequency which is typically 1,000 times smaller than electron spins. Therefore, the polarization of electron spins is much larger than nuclear spins. And now DNP, the goal of DNP is kind of to equilibrate these two populations by very strong microwave driving out of resonance. And in this way, you kind of transfer the polarization of the electron spins to the nuclear spins. And this can provide enhancement factors of hundreds or more. Right? So maybe this picture shows that electron spin polarization is an important thing. It's important for electron spins, but it's also important for nuclear spins, because here you rely on the working, the essential part of DNP is that you have electron spins that are well polarized. So there is an interest, I think, for a general hyperpolarization scheme for electron spins. And in fact, so we believe that Circuit-QED provides such a method, at least partly. And so here's the principle of our method, which is very simple. Imagine we have our sample at 800 milliK. This corresponds to this point on this polarization curve. And we just connect it to a black body radiation at 20 milliK. And so now, essentially, all electron spins can relax by emitting photons. And so they should be polarized to this temperature, even though the sample is at this high temperature. And so one can expect naively that this polarization will be increased by this factor 4, typically, by just doing that. Now, what are the requirements? So this has never been done in magnetic resonance. And why is it that? Why is it? Well, the requirements are that spins should relax radiatively. This should be the dominant relaxation mechanism. Otherwise, you can connect it to a cold radiation source, nothing will happen. Right? So we should be in the Purcell regime. And another thing is that the losses here between the cold load and the spins should be as small as possible, because losses will suppress this effect. And these two aspects are enabled by Circuit-QED. And so we have with Bartolo Albanese, who is in the room, we have set up an experiment to demonstrate this effect. And so we have fabricated an erbium resonator coupled to, again, bismuth donors in silicon that we have attached to the still plate of the dilution refrigerator at 900 milli-K. And now this resonator with the spins is connected to an input line to send the pulses and a switch. And this switch can switch between a hot load, well, hot at 900 milli-K, and a cold load, which is at 20 milli-K, and which is connected to the switch by a superconducting cable. And now, finally, the signal is then sent to a parametric amplifier. This is not necessary for the experiment, but it just provides more signal because we have the parametric amplifier, so why not use it, right? But it could also go directly to a hand. And so these are the data. So maybe first, this is, if you can look at this, these are just two echo signals observed when the switch is connected to the hot load in red and to the cold load in blue. And we see that the echo in the cold load case is indeed larger. And this is this curve here is a T2 curve obtained in both cases. So this T2 decay is, you see that there are many oscillations, more than what I thought, more than what I showed you earlier. This is because in this experiment we have used natural abundance silicon, which has a natural abundance concentration, a 1.1 concentration, sorry, a 4.7% concentration of silicon-29, which means that there is a strong ESEEM signal, even at 100 Gauss. So this is measured at 100 Gauss, and you see this ESEEM signal, but it doesn't matter. What the interesting part is that this T2 curve is really identical when we connect the switch to the cold load. It's just more signal. There is just more echo. So it really shows that there is an increase in polarization by a factor close to 2 when the cold load is connected. So it's only 2. It's not, we would, ideally, if everything was ideal, we should reach a factor 4. But we believe this is due to precisely losses in the setup. And just another curve to also show you this same effect. This is now a spin relaxation curve, both in the hot load case and the cold load case. So here this is the delay. So this is a T1 measurement. This is the spin polarization after a pi pulse and just waiting. So you see that this polarization decreases on the order of a time scale of seconds. And now, if you look at the two curves, you see that the blue curve has a higher amplitude than the red curve. This is expected because the spins are more polarized. But the red curve also decays faster. And in fact, this reduction in decay time is the same as the same factor. The decay time is reduced by the same factor as the polarization when we connect the switch to the hot load case. This is because the relaxation is radiative and now it's taking place in a hot environment. And this is as expected. All right, so let me conclude by maybe the fact that circuit-QED-based EPR spectroscopy enables high sensitivity, and we are really close to the few spin regimes. We would really like to measure individual spins. We hope this will happen soon, but we are not there yet. We have observed some complicated behavior of spins in the presence of strain and electric fields and some mechanisms that need to be better understood. And we are trying to move towards more real-world, more real EPR spectroscopy using more complicated pulses and more complicated samples also. And finally, we are also very interested by this hyperpolarization that opened by the Purcell regime. And I wanted to acknowledge the people who have done the work, and in particular, the Bartolo Albanese, who is present, Vishal Ranjan, who is a postdoc, and former members Audrey Bienfait and Sebastian Probst, who have contributed a lot to what I showed you. Thank you for your attention.